All right, so according to the collision theory, so here's the factors that affect the rate of reaction, okay? So the rate of reaction depends on the number of collision per unit of time per second. So adding more concentration or higher surface area, you increase the number of collision, all right? Adding temperature or increase the temperature also increase the collision because molecules move more quickly, they collide more often. Fraction with sufficient energy, so the activation energy. So reactant have to overcome the activation energy. If the activation energy is low, easy to come by, easy to overcome it. Just like you walk up the hill. If the hill is not as high, it's easy to walk. Okay, so the reaction go quick. If the activation energy is high, reaction goes slow. And lastly, fraction with proper orientation. Yep, all molecules have to collide with the proper orientation. Otherwise, you can't make the product. Okay. Now, catalysts. Let's talk about catalysts. How do catalysts speed up the reaction? Well, catalysts lower the activation energy. Okay. So when you have when a reaction have lower activation energy, so not a lot of energy to overcome, reaction move more quickly. Right? The regular catalyst will do something like this. So lower activation energy, still go with the same route, right? But lower activation energy, so easy to walk past it. Enzyme, which is the biological catalyst, will do something like this. Go to a way different pathway, not like what happening before. Let's say if the red line, that's pathway from water, so oxygen and hydrogen have to collide at a certain orientation. A regular catalyst just lower the activation energy. The proper orientation is still the same thing. But in an enzymatic reaction, so enzyme catalyzed reaction, making water this way are way different from the way that the other catalyst does. Okay, so catalyst reaction, this is an enzymatic reaction. All right. So basically, but in conclusion, all catalysts do the same thing. They lower activation energy, right? The activation energy of this pathway probably just that, really small. We have it here, small, really small, really small, really small, just little thing. All right. Okay. Also, catalyst promotes the proper orientation. I'll show you in a little. Okay. All right. So catalyst and enzyme stabilize the transition state. So here's the reason why the activation energy is lower. Okay. If you still remember what represents at the highest point of the energy diagram, the transition state. All right. So the transition state is really, really unstable. Bond is breaking, bond is forming. Nothing stable there. That's why it has really high high energy level. Now we call activation energy. The catalyst stabilize the transition state. All right, so when the transition state more stable, the activation energy is lower. Basically, that's how it works. So, for example, we use iron to catalyze or speed up the decomposition of hydrogen peroxide. Okay, so this hydrogen peroxide right here comes in. The iron helps pull the hydrogen peroxide molecules apart, and then connect oxygen with oxygen, connect with hydrogen and hydrogen. So you get that. It's come in and come out like that. Okay, so a stabilized transition state in the molecule of the transition state. Also, in the molecules of the catalyst.